Thanks, Dave. If alarm bells aren't going off in your head right now, they should be. Because lending is actually a terrible business, just awful. You know, if you're like a tech analyst, go away. Like, you don't want to be here. But the reason it's so terrible is this what we have come to think of as sort of the trifecta of things that you want in a business that you actually have historically almost never been able to get in credit. Did it disappear? Okay. Well, there were 3 things on the screen. Maybe we can get them back even. Maybe we can go back a slide. You really, out of a credit business, you want to be able to, like any business, you want to be able to grow fast. You want to be able to make money. And interestingly, in credit, you need to make loans that actually will pay you back. You need the credit to perform. And historically, it's become almost a truism that in lending, you actually can't get all 3 of these things at one time. There are some businesses that have managed to get 1, some businesses that have even managed to get 2 out of the 3, but getting all 3 at a time has been almost impossible. And the reason that's true is the reason that Dave stated earlier. Lending is a really old business. It's been around for 5,000 years, as old as human civilization. There are thousands of players in the market competing in an almost perfectly competitive way. It's almost a textbook business where you would expect it to not be possible to get profits without sacrificing something else. That usually comes in the form of growth or credit. Usually something has to give. And that is as close to a fundamental law of the universe as there can be in a business, except for one thing. And that is, if you can actually change the underlying technology assumption in the business, then you can actually release the constraint that makes it impossible to have all 3. So today I hope to show you that what we've built is a large and growing edge in AI that makes this possible. So to understand how that could be, I want to start by giving you a little bit of a history of how consumer credit is done and some of the things that we've done to improve upon it. Because you see, underwriting credit is a very mature discipline, something that's been done, again, for a very long time. There are actually a ton of textbooks on it. It's something you could just go on Amazon and you could essentially get an entire download of how this is done and how you should be doing this. There are very strong industry norms that are reinforced by a network of rating agencies, bank credit committees, loan buyers, regulators, and they all tell you to do very roughly the same thing. And for that, we can just open up one of these textbooks and see what you do to build a credit business. So of course, the first thing you need to do is you need to figure out how you're going to underwrite your consumers. And the very first step of building an underwriting model is called the preliminary scorecard step. And for the preliminary scorecard step, you want to go and find 8 to 15 variables. So not like 20 or 100 or 1,000, that would be too many. You want 8 to 15 variables that you think are likely to predict someone's credit risk. Usually these characteristics have some kind of intuitive relationship with credit. You could easily describe to your friend who knows nothing about this why they're being underwritten this way. And you're going to identify this set of variables. Then you will put those variables inside what is known as a logistic regression, essentially a linear model that when you stick the variables in, give you sort of one weight for each variable. It assumes that there is a linear and independent effect between each of your, call it 10 variables, and the outcome of interest, usually whether the borrower pays the loan back. Then you might think you could just use that linear model, but no, because while, you can read the text here, while it is technically possible to just use this linear model to make decisions, usually for most lenders that would be operationally too complex. So you want to simplify that linear model down into what's known as a scorecard. Prior to working in this industry, I'd never heard the term, but apparently a very common term in the business. And a scorecard looks something like this. A scorecard is essentially a lookup table. It tells you things like if someone has had 0 to 1 delinquencies on their credit file, then you would add 40 points to the amount of risk that you perceive in this loan. Maybe this person has had no inquiries in the last 6 months. That's really good, and you're going to give them 50 points of credit for that. And when you're done with this, you end up with a table of scores and a table of how likely you think the person is to pay back the loan. And on that basis, you will decide whether to give them a loan and what APR to charge for that. Then you'll go ahead and you'll verify their income, their identity, their employment, and you most commonly, like Dave said, you'll do that using documents and phone calls. And that's the industry standard. And that's what we set out to innovate from back when we got started in this business over 10 years ago. So let's see how that timeline played out. 2013, that's sort of the, roughly the state of the world, how credit is done. And it's actually very fortunate that we knew so little about the credit business when we got started. We were in many ways very young, very naive, because we at that time had zero data. We didn't have any of our own training data. And we didn't know that getting to what we now call a calibrated model, meaning loans that perform as you expect them to perform on average, and having a model with enough separation to drive that trifecta of growth, profits, and credit performance was going to be a very long journey. It took us over 5 years to get there. If we knew that at the time, we might have started a different kind of business. But here we are, and so I'm going to take you through a quick history of the technology. I'll just quickly highlight one thing that we did each year between then and now. And I'll do a couple of deep dives to hopefully give you an intuition for how it is that we've created something so different. So 2014, like I said, no training data, didn't have anything, just had to get started. The first thing we did was we looked at third-party academic research for things that might be predictive of credit that were different than sort of what was traditionally used. And we happened upon education data. Things like where someone went to school, what they studied, their highest level of education. And in order to use this data, we had to come up with a whole bunch of clever sort of statistical tricks because, again, no training data, which meant we had to take all these third-party data sets, find ways to join them together and subtract out the covariance. And we made it work. We got a sort of V1 model out the door. And it actually turned out that if you could only choose to have one variable in a model, it wouldn't be FICO. You would actually want to choose something like someone's highest degree or where they went to school. It's actually more predictive of credit outcome than FICO on a one-to-one basis, which is really, really interesting. And because of that, we were able to build a model right out the gate that achieved some very nice separation, at least for a segment of borrowers. But again, with very little training data, our first vintages of loans didn't get properly calibrated, and it would take us many more years to get there. The next year, 2015, we started having just a little bit of our own training data. And importantly, that training data came with these alternative columns, these columns of alternative data that we were uniquely collecting. And so we began to invest in using that data a little more intelligently. Instead of running a single linear model, as was the market standard, we created what's called an ensemble of models. And that basically meant we built a whole bunch of different models. Some were linear, some were not linear. And each had their own strengths and weaknesses and things they were good at. And we took a weighted average of these things based on what each model was good at and how good they were. That of course, improved the model's predictiveness. Then in 2016, you heard Dave talk a lot about our ability to instantly approve borrowers without a whole process. We said, well, let's take some of the same techniques that we've done now in underwriting and apply them to the sort of automation of the process. And of course, that had a lot of advantages, namely that you get a much faster feedback loop to find out if someone is a fraudster, if someone is lying about things on their application, because those applicants tend to default a whole lot sooner. You don't have to wait a full 5 years on a loan to find out if someone is a fraudster, because for better and worse, if they're a fraudster, they tend to not pay you back pretty quickly. And it also was really nice for us that we started with alternative data, because that alternative data turned out to be really useful in building models that could decide whether someone should be approved instantaneously. So consider something like you're trying to figure out if you need to go through the process of verifying somebody's income. It turns out to be really useful to know that a person actually has a verified computer science degree from Carnegie Mellon if what their claim is that they work at Google as a software engineer. Those are highly, highly correlated facts, and having one verified makes the other a whole lot more or less likely. 2017, finally, and this is the year we started using the terms AI and machine learning more publicly, we finally had enough data to start using modern machine learning methods. But we immediately ran into some problems, and those problems are that almost all of the modern machine learning algorithms, especially at the time, but even now, were designed around problems with complete data. And by that I mean, the classic machine learning problem is a problem like classifying images of dogs or cats. So if you're classifying images of dogs or cats, one nice property is that you already know the correct answers. You usually have your data labeled, so you know which ones are dogs, which ones are cats, and you don't, importantly, have to wait 5 years to find out if a picture is a dog or a cat. Now, lending does not, unfortunately, share that property. in lending, you make loans, and it takes a really long time to find out if they were good loans or bad loans. And so we ended up developing a proprietary and now patented technique for adapting the major machine learning algorithms that were out in the open source, things like XGBoost, so that they could deal with this incomplete data problem, and we started underwriting with it. I'll come back to this problem more in a moment. 2018, we took a lot of these machine learning techniques that we were now using in both underwriting and in the automation of the process, and we started applying it to what we call revenue science. We started to optimize the trade-off between conversion and pricing. And that became important because as our models delivered increasing separation of risk, meaning we were able to identify borrowers that we thought were much more or much less risky than traditional models thought, there started to be a large variance in what we call individual rate sensitivity, rate expectations, and how much value Upstart was creating for the consumer compared to their likely alternatives. It just became that for some consumers, we were so much better than anything else they could see in the market. For other borrowers, we were only modestly better, and yet for other borrowers, we were still not the best option. And the right amount of value to try to capture there is very different in each case. Some borrowers came with very different expectations depending on which marketing channels they came from and what kinds of marketing materials they had seen. And so we applied machine learning to this problem. All right, so 2019. This is a really, really important year for us. And we built a framework that was very important and comes back to this problem of some of the unique challenges of dealing with lending in a machine learning context. So I'm going to take you into this one a little deeper, so we'll step out of the timeline. Okay, so 2019, if you go back to that time, that's sort of around the time when machine learning as a discipline and then sort of to this terminology of AI starts to really take off. This graph here is just a graph of the number of academic papers that are sort of ML or AI-centric that are getting published by year. And you can see that the years that our business is getting built coincide with this sort of exponential takeoff in the amount of research going on. I think now it's sort of obvious that this is happening, but at the time, we were around here, and it was really, really starting to take off. And you would think that this would have provided a massive and automatic tailwind for a business like ours that was using this kind of technology to try to reinvent something like lending. But there actually were a lot of challenges. You couldn't use almost any of these things out of the box, and that's because of this problem that I described earlier, where loans have this long-term survival problem. That basically means you make these loans, and it's a little different if you're making loans that are maybe like a week long or 2 weeks long. There's actually a good amount of innovation in these ultra short-term payday style loans because of that. But when you get to these longer loans, you're confronted by this problem that your choices are either you could just throw out all the recent data. You could say, we'll only train models on loans made 5 years ago. Okay, that would solve the problem, but now you've gotten rid of all of the recent years of data, which is probably one, most of your data, and two, most of the most relevant, most recent data. That would be pretty awful. You'd have very stale models. Or you end up having to make some really simplifying assumptions. You could assume that, that if you've observed a certain amount of defaults at, say, month 6, that there would be twice as many at month 12, and 3 times as many by the end of the loan's life. And in fact, that is actually the industry standard. It's called, you create a default timing curve, which basically means you assume some fixed ratio between when the defaults actually happen. And so you can train models on highly incomplete data. Now, earlier, 2 years before this, I mentioned we had started to deal with this problem. At that time, we solved some math problems to just mechanically unlock us using some of these algorithms, but we weren't able to yet grasp all of their advantages because of some of these sort of core survival censoring feedback loop problems. In 2019, we finally did. So we created something that we called the loan month model. And a loan month model is basically something that instead of modeling a single terminal state of the loan, like do you repay the loan at all, we built an architecture that separately predicts default and prepayment in every individual month of a loan's life. That basically meant that instead of having sort of a single prediction we were now making for a 5-year loan 120 distinct predictions. And that meant that we could suddenly start applying all the modern machine learning algorithms to this problem, because each problem was sort of a distinct and completely discrete problem that would be deterministic in what its sort of resolution state was. Now, you might think, oh, okay, that's cute, but does that really matter? And the answer is yes, it matters massively. So I'll just give you a specific example to illustrate the point. So let's take two borrowers. Borrower A has a lifetime chance of defaulting on their loan of 12.65. Another borrower, borrower B, exactly the same lifetime default probability. But what you see in this graph are two curves. The blue curve representing borrower A shows you their default probability in each month of a 60-month loan, and the same for borrower B. And you can see that despite ending up at the same place, this is a cumulative curve, the trajectories they take to get there are radically different. And specifically, they're different in the way that borrower A is a fair bit more likely to default in the first year of the loan's life. Borrower B becomes a fair bit more likely to default in the second half of the loan's life. And this matters a lot, not surprisingly. Now, if you use a traditional approach and you assume a fixed curve, then you're stuck sort of taking something in between, and that's what would happen. You might have an average timing curve as represented by this gray line for your population, and you just assume that's the ratio. That's when I expect that defaults actually happen without having a model that has the ability to sort of make these individualized predictions. But you would get the underwriting terribly wrong, because the actuarially correct APRs for these borrowers turn out to be really, really different, despite having the same probability of paying back the loan. Borrower A's optimal APR, meaning like the actuarially correct thing that solves for your target return with precision, is 16.7%. Borrower B is at 13.09%. And that difference, 361 basis points, is a very large number. And if you're taking a traditional approach here, you're essentially forced to be hundreds of basis points wrong in one direction or the other. And with the loan month model framework, we were able to solve that problem. Okay, so coming back to this timeline, so we were in 2019, we solved some problems. 2020, of course, you see our training data is increasing kind of exponentially now. And with the help of all that sort of background research and background technology development happening in AI, we start to be able to use more and more types of machine learning algorithms. In 2020, we started using neural networks. I think at this point, well understood the value of neural networks, and we were able to start using them after having solved many of the same problems, having enough training data to actually make use of these things. One of the things about more powerful machine learning algorithms is that they're pretty useless and, in fact, quite harmful if you don't have enough training data to support them. So enough training data, enough background research, enough sort of proprietary development of how to make these things work and be compatible with the sort of lending problem, we were able to start using these, and we added them to our ensemble of models. 2021, another area that we started applying AI to was compliance. Now, that probably sounds really odd, a bit counterintuitive, but consumer credit is one of the most heavily regulated industries. And that regulation, especially in recent years, but really forever, it spans policy concerns from fair lending to explainability to safety and soundness in the banking system. There's a whole bunch of different regulators that care about each of these pieces. And that body of regulation has been a pretty significant, major deterrent to sort of players venturing beyond the sort of traditional safe confines of the traditional credit scoring system. You sort of know that if you stick with a traditional credit scoring system, that's already been vetted, it's been used for decades, you're not going to be challenged on whether you are uniquely being unfair to some group, or whether people understand what a credit score is. This has sort of been proven out. And then as soon as you venture beyond that, you're confronted by all of these problems. And if you venture beyond that and you use these very new, very complicated models like the ones we were using, well, you have another problem, which is that almost all of the traditional techniques for managing these kinds of compliance risks didn't immediately work out of the box. So what we had to do was we developed a whole set of new methods, essentially machine learning based methods, to do compliance around things like fair lending and explainability. And we matched the sort of complexity of our underwriting models with equal complexity and sophistication in our compliance systems. And LDAs and SHAP are just two acronyms for some of these systems that we created. Okay, 2022. This thing is one of my personal favorites, so I'm going to do a quick detour to talk about a thing we did there. Now, it's something that Dave thought you all wouldn't appreciate very much because it's just too nerdy, but I think you're going to like it, so we're going to spend some time on this. All right, so this is actually not the cool thing. This is the boring thing. This is like, all machine learning models have something called a loss function, and a loss function is just a fancy term for like it's the sort of it's their goal. It's the thing that they're trying to get as low as possible. They're trying to minimize some amount of error, and this is a very generic loss function, something that like anybody could just like do, and it's present in many of the open source machine learning models. It's called log loss. This basically is just a loss function that lets you represent sort of good and bad outcomes as ones and zeros. And its sort of key properties that, well, you only get ones and zeros in this thing. And so if you like predict something is a 1 and it is a 1, you know, it's really good. And if you predict something's like a 0 and it's a 1, it's really bad. And that's kind of what this loss function measures. And it measures your sort of average error in sort of a log way. Okay. This thing is very nice. It has some really nice mathematical properties, like it makes machine learning models really fast to run. But it has a lot of limitations when you apply it to lending. And it comes back to some of the issues we were talking about earlier. For one thing, it doesn't have a nice way to let you separate the instances where a loan defaults really early and a loan defaults really late. They're kind of just treated the same, again, ones and zeros. It only has one type of 1 and 0, so you're either stuck saying prepayments don't matter at all, or you have to say prepayments are just as bad as defaults. Obviously, they're not. And then the third is it doesn't let you distinguish between the cases where you predicted that a loan would default really early and it actually defaults really late from a case where you predicted a loan will default really early and it defaults just a little bit later, meaning like the sort of amount you're off in time doesn't get well represented, again, when you're in a world of only ones and zeros. Again, now these all sound maybe like, okay, kind of like interesting, but again, like how much does it matter? So I'm going to show you. Okay, so have to explain this graph a little bit. So this is a graph it's a heat map, and what the colors are showing you is a measure of the sort of real error in your financial objectives, specifically the net present value difference of cash flows between what you expected and what you actually got. So this color gradient here, the lower the number means the less error that you've got, the higher the number, more error. And we've color coded it. Blue means you're cold, red means you're hot. You've gotten to a good place with less error, and of course you want as little error as possible. The x-axis is the predicted default in month 1 of a loan, and the y-axis is the predicted default in month 60. Remember, our models have to make 120 predictions for every underwriting. And so in reality, what's happening in the model is this thing, but you're on a 120-dimensional sort of thing, but you can't visualize that, of course, so we've simplified it to 2 for purposes of the illustration. The point is, if you get to the red, then you have less error in the sort of true financial metric, the thing that considers all of the things like, you know, a default in month 1 costs you a lot more than a default in month 60. Getting it wrong by 1 month is a lot less bad than getting it wrong by 50 months. And sort of prepayment costs you a little bit, but not nearly as much as a default does. Okay, so what happens if you use that generic loss function, that log loss thing? Well, this is what happens. So a machine learning model, as I said, follows a loss function, and it follows it along a gradient. It does something called gradient descent, where it's trying to find the values for the model that minimize the loss function. It follows a gradient to do that. So this is actually what happens on the generic loss function here, is that the model starts out here. Its first guess of what the correct parameters, meaning like, it's like, okay, hey, you set a predicted default in month 1 of 5% and month 60 of 10%, and that's its sort of first guess of what the quote-unquote right answer for this borrower is. But then, you know, it sort of says like, no, that's not right, and then it sort of like keeps on looking, and it ends up over here. Okay, pretty good. Like you definitely got from bluer to redder, but you'll notice that its optimization path is just subtly wrong. It doesn't actually get where you really want to go. The reddest location is over there. And you can imagine that when you expand this to 120 dimensions, there's a lot more space to be right or wrong than in just 2. Now, the proprietary loss function that we developed, and this was sort of quite a project. It was a bunch of math and also a bunch of engineering. This actually optimizes along this path. And you can see this gets you a whole lot closer, sort of the place you really want to be, than this does. A very significant difference in both the amount of error you end up with and the actual predictions that the model makes. So, this piece of work, as I said, a very significant piece of work. It took sort of both sort of what we think of as math work and engineering work, because you have to sort of first figure out how to represent the sort of correct loss function as a loss function, and then the second is you have to figure out how to make that thing compatible with gradient descent and sort of fast optimization in a machine learning algorithm, and that's work we did back in 22. All right, so then 2023, we focused on a bit of a different problem, and that was the challenge of applying machine learning algorithms to a business where you have large macroeconomic fluctuations, and therefore the patterns of repayment tend to change over time. You don't really have this problem in other types of machine learning. Dogs always look like dogs, and cats always look like cats. But in lending, the sorts of people that default in this sort of the aggregate level of defaults tends to change quite a bit over time. And that was something that machine learning models naturally didn't handle well, because they treated sort of time as just sort of an unimportant dimension. It was something sort of that you could just not worry about, because sort of all history was equal. And so we invested in making our systems adapt dynamically to changing macro conditions. And so that meant that you would have a system that if there was a change in the world, whether it happened in the aggregate, like twice as many people default this year as last year, or something that happens at some kind of arbitrary segment level, like government employees are sort of under threat, or people who studied English in college are suddenly unable to find jobs, whatever it might be. Like any of those changes are now things that the model could natively and dynamically pick up without any kind of sort of need for upstart staff to get involved. And that essentially means the moment there's a statistically significant trend in the data, our model dynamically responds. And later, I'm going to come back and show you how big of a difference that would have made if we had had that a couple years ago. OK, 2024, one of the forever problems in lending is the problem of adverse selection. The people that want your money are always worse than the people that don't want your money. And that is just always true, kind of unfortunate, but it's what you deal with. And in 2024, we came up with a way to mitigate this problem, and we called that APR as a feature, meaning we literally gave our models APR as a feature to the model. And essentially, that meant that the output of the model, the APR that you want to assign the borrower, is now also an input to the model. And the reason that's a partial solution to this problem is that one of the main avenues of adverse selection is when people are willing to take loans at APRs higher than they should be given their circumstances. So for example, if you have someone who seems to have a really clean credit profile, but they're super happy to take a high APR loan, well, there's something suspicious about that. Probably implies that there's some kind of hidden information that only they have that makes them worse than your model really thinks. The problem technically with doing this is that this is creates kind of an infinite loop. If your output is an input, then the problem can kind of go on forever. And to solve this, we ended up running many parallel instances of our model at once, so that we could actually make the problem converge and resolve in a finite enough time to satisfy our borrower while they're waiting. But in turn, to do that, we had to make a very significant investment in low-level optimizations that we hadn't had to worry too much about before. But suddenly, we had to worry about things like latency, compute, memory, things like that. And in fact, increasingly, as our training data size has grown and the complexity of our models has grown, these lower-level bottlenecks have become increasingly the thing that we've had to solve for. So I'm going to give you an example of one of the things we did in low-level optimization now. So this is like sort of a simplified example of roughly what our training data looks like. You have all these borrowers. They have some attributes from the time that you gave them the loan, things like their credit score and education. And then, because of this loan month framework we have, you have for all of these borrowers, you have one copy for every loan, every month of their loan's life, going up to 60 months. And what that means is that there is actually a lot of repetitive data in the training data matrix, because the data from the time of underwriting doesn't change at all. Like, if we knew that you had a 714 credit score on the day you applied, that 714 never changes. But we have up to 60 rows with exactly these same columns of data stored in them. While we have only part of the matrix that has any unique data, and that's each payment month, of course, you have a different sort of outcome of whether you pay back or not that is unique. But you've got now this interesting thing where you have this big matrix of training data, and some of it has a bunch of repetition in it. So it gave us an opportunity to compress and save on memory. So what we did was we created a new data structure. We called it a block sparse matrix format. And essentially, it involves compressing this data in a way where you only store the unique data, or you only store data that is unique, and the data that repeats you only store once. And you can see that things have been slightly shifted in the data structure, more data represented with zeros. And then we rewrote all of the sort of core machine learning algorithms to support this data structure natively. You can think of it as like they recognize this data structure now, and so that when you ingest this thing with all these zeros, it knows to sort of like use the sort of the unique data in all the places it needs to, despite it not sitting in the matrix. And by doing this, we immediately reduced memory consumption by a factor of 20 today, because that happens to be about the sort of average age of a lot of these loans, 20 months deep. But over time, that actually will grow to a memory savings of a factor of 60, because most of our loans are 60-month loans. So pretty cool win there. All right, so we're almost to the present day, 2025, this year. We shared just a couple of weeks back. We've gotten really excited this year about our work with something called embeddings. We talked about that at earnings, so I won't belabor it, but essentially embeddings are a technique for finding meaning in unstructured data, and they open up the door to using many, many more kinds of data than we previously used. So very excited about that. Okay, so I've spoken a lot about what we did, and I want to turn my attention to the question of whether it matters. Does it matter that we have all of these sort of machine learning techniques that we've developed over the years? Let's say for a moment you believe that we've built at least something a little different than what's classically done. And so to answer this question of does it matter, I'm going to refer back to this framework that Dave laid out, the sort of 5 ways that we apply AI to credit. So I'll start with separation. Separation is the thing we've worked on longest. It is the sort of figuring out which borrowers are more or less likely on a relative basis to default. So I want to first give you a sense of how much separation actually is happening. And the short answer is a lot. So this graph uses some of the same third-party data that Dave referenced earlier. And it is a random sample, just so we could put it on a screen. We randomly sampled some 20-some borrowers. And for each one, we took the range of rates that were observed by industry players, meaning like online sort of like lending platforms. Then we basically plotted in the gray bar the min and the max APR that this particular borrower saw. And then in the teal dot, we showed what Upstart offered them. And the thing I want to point your attention to on this graph is how often, it's really it's surprising even to me, how often the Upstart dot is the lowest or highest dot, very often outside the range entirely on this graph, which means that the rates that we are offering to people look nothing like the rates that they see anywhere else. Sometimes they're way higher, that we think this person is way riskier than anybody else thinks. Sometimes we think they're way less risky than anybody else thinks. So very obvious that a large degree of separation is happening. I think it's about like 70% of the time in this particular sample. We're offering very different rates, at least. Of course, it doesn't tell you yet if that's good different or bad different, but at least very different. Now, to find out if it's good or bad, we've got to start looking at some of the outcomes. So we'll start with a single illustrative example of a borrower, and then we'll show you it with more data. So a specific person 5 years ago applied for credit. These were some of the facts about them that a traditional model saw, and what the traditional benchmark model that we hold internally for calibration would have said. So this person had a mid sort of 600s FICO score, kind of on the border between like sort of non-prime and kind of mid-prime. They only had about 5 years of credit history, and they only had about $60,000 of income. Not a particularly prime borrower. This person, a traditional model, very likely turns down. And our version of a traditional model said their likelihood of defaulting is about 32%. That's a model built using the textbook techniques that I described at the beginning. Pretty likely to not pay back on a 5-year large installment loan. Here's what the Upstart model saw, something radically different. We saw that this person had a JD from the University of Pittsburgh. They were working as a lawyer for the city of Philadelphia. So even though their income wasn't super high, they had a fair bit of stability to it. And their debt use was extremely low relative to other people in similar circumstances. We took, of course, those facts, ran it through all those models, and we ended up with predictions for, again, every month of a 60-month term for default and prepayment. And in aggregate, the model said, we thought, in contrast to that 32% likelihood of defaulting in the traditional model, we thought there was only a 2% chance that this person would default. So not only should we give this person a loan, we should give them a really good loan. And then what happened? Well, this was our set of predictions for each month of default and prepayment, the black line being predicted defaults by month, the teal line being predicted prepayments by month. And this borrower actually made 21 on-time payments before fully paying off the loan, prepaying in month 22, right around the time that our sort of by-month prepayment curve was going up. So a success. This was a good loan to have had separation on. Now, of course, that's just one loan. Let's now repeat that exercise with a bunch of loans. So we've sort of randomly sampled a couple hundred loans back from 2020 so that they're fully played out. And what we've done is we've gone ahead and ranked them using a traditional model up on top and an Upstart model on bottom. So these little icons here are real people that applied for loans back in 2020. And this means that this person was the top ranked person by the Upstart model. That person was the top ranked person by the traditional model. And the colors tell you whether those people ended up actually paying back their loans or not. Gray means they paid back. Red means they did not pay back. And with this set of risk rankings, the amount of separation that you've got, if you're using these models as a lender, you have some choices to make about where you set your approval rate. So let's say that you do a simple thing. You say, I want to approve the better half of people, and you approve half the population. Well, in that case, with a traditional model, you have an approval rate of 50%, and you end up with a default rate of 9%. If you were to use the Upstart model instead, you have an approval rate of 50%, and you end up with a default rate of 5%. It's just sort of basic math because if you have better separation, then at the same approval rate, you can solve for a way lower loss rate. Now, usually what happens, though, is that it's not exactly, it doesn't play out like this because people want to solve for a certain acceptable default rate in their business. So let's say you wanted to normalize these, and maybe as sort of a traditional player, you want to get your default rate down a little bit. To get it down, say you want to get it down to 7.5%, you have to cut your approval rate because mathematically the only way to do that, given this is the best ranking you can produce, is to just pull that yellow approval box in until your approval rate gets down to 7.5. Or sorry, your default rate gets down to 7.5. And to do that, you end up here with a 27% approval rate. So a very significant reduction in your approval rate. By contrast, when you're running the Upstart model, because the degree of separation in your risk ranking is so much better, to solve for that same 7.5% default rate, you can bring your approval rate all the way up to 67%. And again, this is just illustrative, but it is a random sample, so fairly representative. A very large difference in approvability of the population at the same level of risk because of that better separation. Now, automation. This is something we've talked a lot about, but we started doing instant approval back in 2016, back in the timeline. And within a couple years, it had become extremely important to us. In 2018, it was 40% of our loans were fully automated, and that number would keep going up to the number that you now see, which is about 90%. And when you look under the hood, the reason that became so important to us is that there's a massive difference in the conversion rate of loans that are automatically approved versus manually reviewed. There's probably no single thing that you could do that's more important to whether a borrower is likely to actually take your product than to automatically approve them. The conversion rate is about 3 times the level compared to if you send them through manual review. And that's great news. But the reason it's even better news is that one thing you might think about this 90% metric is that it's sort of done going up. Like it can't really go any higher. And the sort of secret, weird, counterintuitive good news about having a really high conversion delta between people that are fully automated and people that are manually reviewed is that when we have 90% of our loans fully automated, it actually means that only about 75% of the applications are fully automated. And that's because they convert so much better that they end up being a larger portion of the end loans. But it means that the opportunity is not to go up from 90, it's to go up from 75. And we expect that this number will continue to rise and as we pour more ML attention into automation. Okay, calibration. This is a pretty juicy one, and I think a topic that is very top of mind because of the events of the last few years. So calibration is, by the way, just the term we use to refer to whether you get the aggregate level of defaults predicted right. It's sort of what if you were a loan buyer or someone that was holding the sort of end risk of the loans, what you really care about. So if we look back at what happened in the industry in the last few years, we see something really stark, a reminder that credit is a pretty terrible business. Because one of the terrible things about credit is that it's very subject to macro forces. It's very volatile, and you get these sort of times when everything's great and times when everything becomes terrible. And that's really what happened over the last few years. So if you rewind back to early 2021, we had a relatively low level of defaults. And this is data for the whole industry, by the way, not like Upstart specific in any way. This comes from TransUnion. It's just on the entirety of what TransUnion sees for personal loans, credit cards, and auto loans. And in the last few years, we saw a 50% rise, industry aggregate rise in personal loan delinquencies, 40% rise in auto loan delinquencies, 70% rise in credit card delinquencies across the entire industry, really in a relatively short time. This measures start to end, but if you just measured even like from 2021 to 2022, like you would see that same rise. And we got hit by that too. We got hit starting early 2022 when that curve really starts to go up. And the way that manifested is that our loans coming out of the Upstart ecosystem in Q1 2022 had a very large what we call loss variance. That means that the realized defaults divided by the predicted defaults on that vintage of loans was 59% in excess of what we predicted. And you can see that this loan underperformance persists for a whole bunch of quarters, because as that graph continues to go up and persists, and our machine learning models take time to calibrate, it says, well, all history is created equal, so we're not quite sure, is this the new normal? Maybe, we should sort of take a weighted average of the new period and the old period. That's the sorts of things that, machine learning models naturally do. It takes 1, 2, 3, 4, 5, 6, 7, 8, 9 quarters until you get a vintage of loans that is fully calibrated. Now, in response to that, we started investing, as I said, in what we call dynamic macro handling, giving our models the ability to, in real time, respond to macro changes and giving the model what we call time as a feature, meaning telling our models that not all years are created equal, and that time is something you can actually use in combination with any arbitrary characteristic of loans to understand what's changing about the world. And by doing that and building certain techniques to make our models train and update much faster, we're able to now backtest what would have happened if we had our state-of-the-art systems back when this all played out. So with those new systems in place, we would, in Q1 of 2022, have immediately started seeing our models respond to the training data. They still would think that it's not totally obvious if it's here to stay. And as those curves are really steep, there would be 2 quarters where you would still have underperformance. You have eliminated the majority of the underperformance immediately, but you would still have some. But within just 3 quarters, you start getting very significant reductions in the loss variance. And by the end of the very first year of the turn in the credit cycle, we go from a sort of real history where we had 41% of excess loss variance to right where we want to be, which is right around or below 0%, meaning that there are actually just slightly fewer realized defaults than we predicted, which is where we like to sit. And that effect persists through the entire rest of the time series here. So really powerful stuff, and it makes us very optimistic that in the ability to handle sort of generalized turns of the credit cycle, because there's nothing about what we put in place here that was specific to 2022 or the specific way that the end of stimulus effect played out. It's all just sort of native machine learning stuff, and it all it sees is actually just data. All right. How does this generalize to our new products? This is a pretty important question, because increasingly we are getting away from just one product into the sort of entire set of consumer credit products. So the list of things that I described in the timeline, again, those are just a sample of things, but I think, again, for purposes of understanding how far along we are on the journey to generalization, it's useful. Here I've got the sort of 4 new products that we have today: small dollar relief lending, auto refi, auto retail, and HELOC. And I'm showing you where we are in the journey of generalizing all of the work that we've done to apply to these new areas. In small dollar lending, we've got basically everything. And that's because small dollar lending has a lot of training data, because those loans are small, but they're very numerous and are contributing a very significant number of new borrowers to our ecosystem today. It also means it has enough training data to support virtually all of these techniques. Auto refi is our oldest new product and has been around the longest, so it's picked up most of these techniques, but it still needs a little more training data before it can usefully use all of these things. Auto retail and HELOC are relatively newer. They're still a couple steps away, but they will get there. And the great news about this setup is that essentially, unlike in personal loans, where each time we had to develop brand new novel techniques to be able to move the models forward, here we already have all of them, and we're just sort of waiting for, like, you need to have 100,000 like HELOC loans before you can use certain techniques, and maybe a million before you can use other techniques. But there's essentially a long runway of proven techniques that will increase the separation, improve the calibration, increase the automation of each of these products as they hit enough scale to use them. Lastly, personalization. This is kind of the new frontier for us. It's just a new frontier, so I'll be brief and just give you a bit of a glimpse into the kinds of things that we're working on here. So the general fact that motivates this whole area of research is that there is a very clear relationship between reducing charge-offs and increasing revenue in our business. That's maybe not surprising, because we're in the business, of course, of facilitating credit. And when there are less charge-offs, more people can be approved for loans at lower rates, more people take the loans. And that relationship is very roughly a sort of 1% to 1% relative basis. Now, in order to go after that, there are a whole bunch of different things that we can do, starting with the way that we service loans that are facing some kind of delinquency. There are things that every player in credit does today, loan modifications and debt settlement, that are done with essentially fixed rules, meaning like when borrowers have sort of circumstances X, Y, and Z, we allow them to get a loan modification, or when they are a certain number of days late, and then we will settle the debt at certain terms. But those modifications and settlements are not individualized in any way, meaning they're not targeted. So that means that there is both the person who just lost their job but otherwise was an entirely good faith borrower who's getting a loan modification, and the person who's opportunistically using it as a way to defer making payments so that they can maybe buy another round of expensive goods that they want to buy. A similar story in debt settlement. And in spite of this, debt settlement and loan modifications are very positive to the returns of loans. That's why we and everybody else have them in our set of tools. But they're positive despite the fact that you're netting out a population for whom it's very useful and a population for whom it's actively harmful. And of course, the promise of machine learning is separation, that we could separate these two populations and just give modifications and debt settlements to the people that would really actually benefit from it, and avoid giving it to those who would not. And of course, you can go one step beyond that, and you can do it for the specific types of modifications and settlements, the specific amounts, and so on and so forth. Very easy to imagine you could get a very meaningful reduction in charge-offs from this, since essentially every borrower that ends up defaulting will pass through some of these processes. Then there's the sort of standard interventions you do. Interventions are things like, at the low end, you have phone calls, emails, texts, you can send people mail. At the high-end touch, you can imagine some people actually need debt counseling. Like they have too much debt, they need help with sort of how to manage their finances, how much spending, budgeting, all of this stuff. But you don't want to spend that amount of money on everybody. It just would make servicing not work. So again, targeting is the name of the game. You can optimize payment due dates, and so that you can sort of draw money when it's most likely to be there in relation to payday, et cetera, et cetera. And you can match borrowers and agents so that the best people to talk to a particular borrower are in fact the people that will talk to them. And of course, the sort of holy grail of it all is that you can actually build AI agent servicing to dramatically change the cost structure. And not really in the service of cutting costs, which is sort of nice, but really so that you can use those dollars towards high-cost interventions on people where will really make a difference in reducing the number of defaults. That's where the high-leverage financial play is. So with all that, with all sort of 5 areas of AI, we believe that within just a couple years here, AI is going to enable us to have achieved all 3 legs of the credit triangle and to have done so across all the major categories of consumer credit across their whole life cycle. That means to consumers, we'll have the best rates and the best process for every type of credit. And the gap between us and the next best option is going to grow rapidly because all this is supported by a uniquely profitable business model that, again, is very hard to achieve in lending given the dynamics of the market. We've got these compounding technology wins in algorithms and data, and we'll have a full lifecycle consumer ecosystem. And with that, we will go to a break, and afterwards, Chantal will be back to tell you about our consumer brand. Thank you.
Please welcome Chief Marketing Officer and SVP of